Well, yeah. All right. Is that you, Joe? Good to see you. Thanks for inviting me back again. I've got a use after free mitigation to bypass, which I guess breaks Dave's rule of keeping it simple, since it's kind of not. But, you know, it's kind of interesting. He talked about how it's got to be either social or technical, social instead of technical, or simple instead of, but it's actually everything, right? It is a technical problem. It is a social problem. It's both. And it is simple and it is difficult. It's neither, I don't think you can quite simplify it in that way, right? It's everything. It's all the above when it comes to technology because it's evasive, it's everywhere, and it's just crazy how much it's invaded our lives as far as where technology is. So I'm Jared. I think a lot of people here know me, so I'm going to kind of skip that. I wanted to look at this new protections that are in Internet Explorer for a lot of reasons. One of the reasons is I kind of have a history of doing that. I looked into and helped even kind of shape some of what became of Emmett and kind of talked about some of the bypasses against it last year, so maybe you saw that. So I kind of wanted to look at the new protections that were in Internet Explorer as it relates to use after free, and I'll talk a little bit about all that. So one thing I wanted to do real quick, in case you're not, as up to speed on this whole memory corruption thing, is just do a real fast summary of the different attacks that have been against various things like stack smash and stack cookie. So if you look at a real simple example, you have like some local buffer, and the way that was exploited is when a stack frame is set up, some malicious copy created a situation where you could change the return pointer. And the way that was fixed was basically by the compiler can insert what's called a stack cookie, and then that's checked before and after the frame to make sure it's the same. So that's the reason I want to give some of this background is I want us to think about, okay, if there's a problem with the way that code is written and the way that code ultimately is compiled and deployed such that an attacker can change the flow of execution or something like that, what are some of the ways in the past where we've dealt with that, and how does that shape how things are happening in the future? Likewise, we had a situation in the past where those stack cookies weren't any good anymore. And one situation where that would be is if you had a very long stack overflow, what you could do, this was a traditional heap spray against a browser that was kind of popular in the 2007 timeframe, is you could basically fill up the heap with a whole bunch of nops and shellcode, and then you could trigger a stack overflow so long that you hit the end of the stack, which caused an exception, and you had overwritten the exception handler, and then you could go to your shellcode on the heap. So the stack cookie was never checked because the function never returned. So that was, you sort of have this situation where we had a problem, we fixed the problem, now we have a problem again, right? And we see that over and over and over again, and that's kind of the thing I want us to think about. But if you had ASLR and DEP, maybe that would solve this issue, right? For example, DEP wouldn't allow that code to execute on the heap, so maybe we can solve it again. Until something like ROP comes along, and basically what the typical way to exploit a ROP deal is, okay, so we have DEP, which marks the stack or individual pages really, the stack or the heap memory, which should only either be read-write or read-execute, but generally not both. What you can do as an attacker is if you have some heap overflow or something, you can pivot the stack pointer off the stack onto the heap, and you can call your code reuse attack, which return-oriented programming is one of those code reuse things. So if you're not familiar with ROP, I don't have time to go over it, but basically to visualize what happens is you return to some location like instruction 7, you do something, and then you hit a ret, which triggers the next instruction in this whole sequence of gadgets called a ROP chain. That's kind of how that works. So the way we want to deal with ROP is essentially ASLR and DEP such that you don't know the address of any module, right? So if ASLR and DEP actually work, then you don't know the address of a module, you can't create a functioning ROP chain. Unfortunately, ASLR has been sort of challenging to get right historically. Third-party libraries, DLLs, were slow to adopt. It was an opt-in protection like many newer Visual Studio protection. There's another new Visual Studio protection called CFG that I might talk about if I have time. Those tend to be opt-in because you have to deal with existing code, right? So you have to always account for legacy, essentially. There were other problems with ASL. There were other parts of shared memory that were known, even if all the DLLs opted in. And even recently, if you look carefully at some of the CVEs that have been coming out this last year, some of them will say things like, resolved an issue with ASLR and IE. and that's all it'll say, right? It won't go into much detail if you look at like the Microsoft Bulletin or something. But so it's clear that, even now that's still challenging, but it's getting better. ASLR is pretty good now, but it's getting better, and it's taking some time. So one of the things that came out to help deal with ROP on Windows platforms anyway was Emmet. And there's tools like Emmet, other types of basically what they are is userland anti-exploit toolkit type protections where you inject a DLL and you do some extra magic, which hopefully will notice a ROP attack and cut it short from allowing it to finish. And I talked about that here last year. One of the ways to get around some of what Emmet does, for example, one of the protections of the 5 ROP checks in Emmet, it basically would check to make sure that the stack pointer was actually on the stack. That was called the stack pivot protector. And so what we did to bypass that was we basically just took our input, which came in on the heap, and we copied it all to stack. And then we triggered whatever we needed to do from the stack so that the stack pointer, we could pivot it away originally and then unpivot it before we called whatever critical API was checked. So that's basically the background as far as that goes. So ROP lives on despite ASLR and DEP, despite Emmet. And one of the things that's facilitated this continued abuse has been the bug called use after free. Okay? And we'll talk about what a use after free is and how it works and how we can maybe stop that. That's what this whole talk really is about. So one sort of high-level slide as we think about points at which to stop an attack. So if somebody is going to attack your endpoint, your laptop, which we call an endpoint, right, or whatever it is your endpoint is, your application could be coded in especially as far as this. So I'm really only talking about memory corruption bugs here, right? So injecting code, shell code through some memory corruption. If you've got some other issue where somebody can just walk up and there's no user and pass or something, I'm not really talking about that, right? So I'm not talking about design bugs really at all in this sense, but mostly directly talking about memory corruption stuff. If it were coded in a safer language, that would help a lot and be pretty easy. If not, maybe there's other things in code you can do, like you can use smart pointers or some other way to manage the life cycle of objects, which would help with the use after free bug. If not, maybe ASLR and DEP will help. If not, maybe Emmet will help. But at this point, you're kind of in a bad situation because a user attack is essentially running at this point, right? So Emmet injects a DLL in your process, malicious attacker injects shellcode in your process, and they're sort of fighting for equal ground. And then the absolute worst place to try to stop an attack on your host is basically after the attack is running, you've got AV or something that's going to notice this attack that's running and shut it down and clear your computer, right? Because it's been proven time and time again that, malware can disable AV or whatever it is, right? So that's kind of the least ideal place to try to stop an attack. And so I just kind of point that out to make sure that I have some high-level stuff in my talk as well, and kind of, if you don't catch everything down in the weeds, maybe you'll remember at least some of that stuff. So what I really want to talk about today are 2 new protections that came out to deal with use after freeze called isolated heap and delayed free. So that's kind of what the topic of conversation really is about. And use after free, if you haven't been following all the Operation Snowman and Operation Clandestine Fox and all these ridiculous names, most of those operations, APT Operation 47 or whatever, were facilitated by a use after free bug in a browser, generally IE or whatever. So it's a big problem, to make a long story short. And the way it works is you have an object, and this object lives somewhere in memory, presumably in your browser. That's kind of what I'm talking about mostly in this, because these protections are in IE, right? So I'm really talking about the browser essentially right now. And this object then gets somehow unexpectedly freed. And it's not surprising that this happens in browser, because with a browser, there's basically a disconnect between what happens in JavaScript and what the browser is doing. So the browser has got all these objects and code and stuff running and stuff in memory and everything, and then all of a sudden it connects to a web page, and the web page goes, do this, right, JavaScript. It programmatically tells your browser what to do via JavaScript. So there's a little bit of this disconnect. So if your browser allocates an object, and then somehow through JavaScript you're able to free that, and you know that, then you can refill that memory with your own payload just by allocating a string or something, and it'll end up in that same spot. And allocators do that, by the way, in case you wonder why would it end up in the exact same spot. The reason that happens is basically allocators don't want memory to fragment. Just like with your old hard drives and stuff, you don't want big gaps in your hard drive where files used to live. You want to unfragment that. you don't have to do that with a good allocator, because basically if it just freed memory for like 50 bytes and somebody asked for 50 bytes, it's like, oh, I have a hole waiting for you right here. So it's by the nature of the efficiency of the allocator that this happens. And then, of course, when the legitimate code tries to call a method on that object, which has now been essentially changed underneath the hood, when it tries to free it or anything like that, bad things will happen. It'll facilitate one of the three primitives that we need to actually allow for an exploit to take place, like an arbitrary read, write, or execute, and probably all three is what you need, generally speaking, today, because you have to deal with ASLR and DEP and all this other crazy stuff. Like I said, the allocator sort of facilitates this. Why does this really happen? So the other why does this really happen is just the nature of complexity of code, right? So if you think about C and C++ code, which is really what I'm talking about now, and memory corruption bugs in general, people generally aren't writing C code for their cafeteria menu or something like that, right? Or they shouldn't be. If they are, it's like, oh my gosh, why are they doing this? They should be using .NET, C#, something else, right? Like don't use C and C++ at all, just in general. But it still get used because you have to use it. You need it for kernels, you need it for browsers, you need it for hypervisors, you need it for all this crazy stuff that's still getting written. And all those things that are still getting written are very non-trivial applications like a browser. They're very complex. And they have this impossibly complex life cycle of objects essentially within them. So stuff gets created, stuff disappears. Stuff is being allocated and deallocated all the time, just depending on whether it's rendering or pictures or font. Who knows what's happening, right? Based on whatever the application is doing, it's complex under the hood. And so because of these complex workflows, the life cycle of objects is hard to account for. It's hard to pinpoint when this object should be alive and when maybe it's valid for it to go away. And if it happens to go away before that, we're in trouble because we might use it again accidentally. And that particularly is a problem when you're using what's called naked or bare pointers or raw pointers or bare naked raw pointers. I don't know if that's a term or not. But so you can use this other thing which is called smart pointers, which basically, generally speaking, if you allocate an object with new, then you need to delete it later. But if you tried to do something in between which caused an exception, which also freed it, and you try to double free it, basically when you try to delete it, that is essentially a use after free. So bad things could happen. Where with a smart pointer, the idea is that the object manages its own life cycle, and it'll go away when it goes out of scope. There's usually some scope. So when that routine finishes or whatever it is, that object just goes away. And if it happens to go away before that, that's fine because the reference count goes to 0, the object goes away, and it'll never try to go away again twice. At least that's the idea, but it's never quite that easy. With C and C++, everything's sort of very complicated. Smart pointers are supposed to help with this use after free problem, but they don't always for a lot of reasons. Some of the reasons might be that Windows APIs that you need to actually use throughout your code aren't smart pointer friendly, so they still basically need a raw pointer as far as a parameter that's passed to them. So you end up rawing into your smart pointers anyway. And so there's all these places in code where if you look through complex code bases, you go, oh my gosh, this is ugly. And I can see why this didn't help, and I can see why that happened. So one of the things that Microsoft wanted to do was say, okay, so we've got all these protections, right? We're using smart pointers, we've got Emmet, we've got ASLR and DEP, we've got all this stuff, but we're still having problems with use after free. We need to do more. And one of the more is that it's not that difficult, at least conceptually, to create another heap. You can just do heap create, and I'll just show that basically on the next slide. You just call this function heap create, and you've got a handle to another heap. So not a problem. To keep your default, whatever used to live on the default heap, you can keep certain things there. And for other objects, particularly objects you've had trouble with in the past, you can create another heap and you can allocate those objects to that heap, such that if one of those goes away, generally the normal way that we attack a use after free is by allocating a string in JavaScript or something. That string will end up on the default heap, not the isolated heap. So even though this use after free problem didn't necessarily get fixed from it might still crash or something, at least you can't exploit it. Is kind of the idea behind the isolated heap. And there's a number, if you're familiar with the DLL, the critical DLL in IE is ms.html.dll. That's basically the DLL that does everything in IE. And these are some of the objects that live in that DLL, the C element objects, for example, and others. Those all end up on the isolated heap now. And we'll see some examples of that. And so one of the things I did was I wrote a Python script, which I released already. that basically just enumerates the IDB from IDAPRO and just finds all the different allocations and says these are all the ones that live on the isolated heap that are this size, these are all the ones that live on the default heap that are this size. So it can sort of help you if you're trying to figure out, this, for example, the C text area element object used to be on the process heap, and now it's on the isolated heap, and it's really easy to tell. It's not hard to figure that out in disassembly because the symbols are there essentially. And you can see clearly that it's the same size, same object, just goes to a different heap now. So nothing too crazy there, really. So unfortunately, that's not enough, and we'll see why, to just separate the heaps. So they also basically, just kind of like DEP isn't great alone without ASLR, and ASLR is not great without DEP. You kind of need both for it to work well. It's the same situation here. You need both of these kind of working well together for this to actually have a positive effect on fixing the UAF problem. And delayed free is the second of those two. And basically what happens normally when you call heap free on an object is that object gets released right away and it's ready for another object to come take that hole. And the idea with delayed free is like, well, if I'm about to release this object, fine, but let me hang on to it for a while. And just in case somebody else tries to grab it again real quick, I'm just going to hold it. I'll zero it out. So if somebody tries to use it, basically what will happen is you'll have a null pointer exception. Something tries to dereference a value inside of there, it'll crash on all zeros. But there won't be any possibility in the short term. So I sort of came up with an analogy of school ground children, and the way the analogy I sort of used was basically, you try to separate the good kids and the bad kids. That's the isolated heap, right? And already you can see that that's a hard problem, right? Because kids aren't generally good or bad. They could be both someday. Maybe they're good one day and bad the next. So it's not an easy thing to do, and that problem ends up happening in the heap allocator as well. It's not always clear, should this object live on this heap or that? It's not always an easy thing to cleanly separate objects. And then the delayed free thing is sort of like if all the kids are standing in line to get inside the school and one of them has to leave to go use the restroom or something, the teacher basically says, I'm going to watch this spot for a while. That's kind of the delayed free thing. So that because what the other kids want to do is they want to cut in line, right? They want to get ahead of the other children. But the obvious issue there is that the teacher has limited resources and she can't watch that one spot forever. So we can see that neither one of these approaches is perfect, but together maybe they're helpful. That's kind of the idea of combining these two approaches. So what gets created on a per thread basis is an object called the C memory protector, and it holds essentially some metadata about the total size of all the things we're hanging on to for the delayed free. And basically it's a big list of all the blocks that we're holding on to, the address and the size. And the last 2 bits of the address get used for other metadata as well, just like they sort of do in actual heap allocators. So it's sort of like a custom memory deallocator, really, if you kind of think of it that way. Okay, so what happens is basically there's this protected free function which will run when you try to free it, when you free an object. And what happens is that if the size of all the chunks you have now is greater than 100,000 bytes, that's when we'll call the mark and reclaim. Or if this mark and reclaim flag is set, or let's see, try to remember. I got a lot of notes on this one. So basically, what will happen is when you free an object, it'll look through this list, add it to the total size, add it to the count of the things in the list, but it won't ever try to free the one you just added now. Basically, there needs to be another sweep for that to happen. And if it's an isolated chunk, bit 1 will be set. So make a long story short without kind of getting bogged down in all the algorithmic details. There's an algorithm behind how things are freed, and these are some of the details of it, which have been made public on our blog, so you can go and get these slides later if you want to kind of dig back through it. Okay, so likewise with the mark and reclaim, what happens is we'll first sort the chunks that are in the list, and then check to see if there's any references to the chunks that we want to free still on the stack, and if there are, we won't actually free it. Those will be marked. So the reclaim unmarked blocks basically says for any of the blocks that are in my list, whenever I call this, go ahead and actually free those if they're not marked. And the size is, so there's a certain situations when this will get called, like when the size of the total list is 100,000 bytes. And then clear the bits the 0 bit as well, because that'll get reset. It'll do a research on every block every time, basically, to make sure to see next time this routine is called, are there still pointers on the stack pointing to this piece of memory. So basically it's kind of trying to figure out, when do I really let go of this memory? And of course, that has to happen unconditionally at some point, otherwise you end up in this situation of essentially a giant memory leak, right, where you're just holding on to too much memory and you need to finally let go. And so the main way that happens is when the stack frame for this current thread fully unwinds to where it started, then it knows that whatever was being done by this piece of code is done, so I can release all the memory I'm hanging on to. And so that's basically what I call the potential, and really that's the big finding from this research, is the potential for a long-lived reference to bypass these type of protections. So any short-lived references, if you are inside of a function, a big class member function or whatever it is, and you free a piece of memory, and then inside of there you use it again, that's the typical UAF that happened a lot in IE. That situation is essentially protected because you had a reference to that object or whatever it is when that stack frame entered. That memory won't actually be freed at that point. But if it's not until basically a long time later, when that whole stack frame is unwound, you're not in that routine anymore, you're way off doing something different, then there's a potential for a use after free to really take place, because it will have really been freed by then. Okay. So how effective are the protections? Basically what I did was looked at 4 different UAFs, and that was enough for me, because digging into each use after free bug takes quite some time anyway. I mean, really, when you're doing research like this, if you want to figure out what changed between this protection and that, maybe you'd want to look at 100 different bugs or something to really get some statistical interestingness. But it's a bit of a challenge to set up, find the vulnerable version of the browser and find the actual POC for that attack and figure out how it works. Because I had to figure out specific things to do this sort of testing, like figure out what object was being used after freed and where did it happen, basically where was it allocated, where was the fault location, what was the size of the object in question, and what heap did it live on before and after the protection. So that was kind of the things that I wanted to track. And interestingly enough, we see that 2 of the 4 still live on the default heap even after the isolated heap was put in place. So that gives you an idea that cleanly separating this object goes to this heap and this one goes to this is not always a trivial thing, right? Okay. I think I said most of this, basically talking about how some of the features of isolated heap and deferred free and how they need to be used in combination. In terms of a bypass, it's really easy to fill up that list such that there's 100,000 bytes waiting to be freed. So you can basically force that condition in JavaScript whenever you want, as a malicious server, right? So that's easy. Finding objects on both the isolated and default heap, which could be of interest, is relatively straightforward. So that's not too hard. The only bit that's really quite hard to bypass is if you have a bug that uses the object shortly after it's freed. The delayed free really messes that up and makes that difficult. So here's some JavaScript to basically make sure that there's 100K bytes waiting on the list. You can just allocate a bunch of objects and then free them. So that part's super trivial to you can create that situation anytime you want in JavaScript. There were some other esoteric ideas as far as bypassing this protection. Like if you had some other corruption bug, you could maybe change, you could zero out references on the stack or something. But if you have a really good corruption bug, then you don't really need to do this. So I kind of stayed focused on really trying to understand these protections as it related to what was really taking place here. So let's look at a few example bugs. There was one a few years back in the C MSHTML ed object, and basically in JavaScript you call this exec command, and it creates this object of a certain size. Doesn't matter really for this point because you could replace it with whatever it was. And then as an attacker, you basically set up your code, your malicious web page, such that an event will get called right away, and then you wipe out the page with this document.write, which is a line of JavaScript code that you can call anytime, and that freed that object, and then when you return from the event handler, you tried to use the object again, not realizing that it had been freed. So, and that's a pretty typical situation. That's essentially the crux of many of the UAFs you see in browser land are somehow related to event handling or something like that, where you were about to do something and then, oh, I got to go do this. Things change, and then you go back to finish whatever it is you were doing, and now your object state has been sort of moved underneath you. And a real simple POC of this would basically look like the body is on load, you call function B, which basically makes sure that the object in question is allocated. And then the first thing it does is this select all. So on select, which is the event. So it gets called, it gets created. It's like, oh yeah, by the way, you select everything. And so when everything gets selected, that's basically the same thing as basically manually selecting the whole web page with your mouse. It sort of automates that same thing. And then as soon as all the select all takes place, you do this document.write inside that select, which basically erases the current DOM, the structures inside the current web page. So it's basically like automating simple things, you know, like highlighting and deleting a page sort of like, but it's doing it in a way programmatically such that, and by the way, as soon as you delete it, you can force free and spray, which fills that space back up with stuff that you control, and then when that function exits and goes back to where it was, then it's where you have the use again. So how do you debug UAFs? Like if you're in charge of, you know, a browser crash or something, and you're trying to figure out is it exploitable, or you want to write an exploit, or you're trying to figure out how these things really work, what's the process like behind, you know, working in a debugger such that you can understand these kind of bugs? Basically, step one is either in IDA Pro or WinDebug, you need to learn something about the object, figure out what the object is, what its size is, what it does would help. You need to that's one reason that UAFs have been kind of a pain, because for trivial security bugs, like if you think back to like a simple Stack Overflow or something where somebody just did an unbounded stir copy or something, from a developer standpoint, it's like, oh, I can fix that. Just change the size to be smaller or make it a stir n copy, or like the fix is trivial, right, from a developer standpoint. But in these cases, the fix may or may not be trivial. It may still be difficult, whether you have the source code or not. It may be difficult when you get a crash. You'll go, okay, it crashed here. I don't know why it crashed here. And that's pretty typical when you look at these sort of crashes when you first look at them. Rather, even if you have the source code, you go, I'm not quite sure why the program crashed at this point. It's because there's some object lifecycle problem, and you have to figure out what that was. And so it's not really that much harder without the code, basically, which is the kind of the good point for the attacker. So it's kind of bad, really, from a software security standpoint. These bugs are kind of a pain to deal with. So you have to figure out what the object is, and then you can use some of these gflags abilities in Windows, particularly, where you do gflags -i iexplore.exe plus HPA, which is the debug heap. So basically saying every time this process runs, instead of using the regular heap allocator, use the debug heap, and also enable extra stack trace as well. So then when you get a crash inside WinDebug, you can do this command, bang heap -p-a address, and you get extra information about the allocation. Basically, this memory address was allocated via this call stack. So you can figure out, oh, this sequence event led to this object being created. And then you can do the same thing both for free and create. You need to figure out, okay, this is generally how it was created. This was generally how it was freed. And this is where it crashes. And then you basically put all three of those stack traces next to each other, and you draw a line across where they're the same, where like the lowest common denominator, where they're all the same. And then at the point above that line is where you can actually begin to understand where things went wrong. So that's kind of the debugging process. So if we look at this crash for this particular bug in WinDebug, where we didn't have, so the original, anytime you see the word for these next four examples, the word original, it just means we don't have isolated heap and delayed free. It's as it was before those protections were put in place. In the original case, we see that this bug worked, and worked in this case is basically I'm just showing that we have some proof of concept that we can control the contents of the register or a register that gets dereferenced. In this case, we see all these 39, 39, 39. And now it would be in JavaScript, it's just 9999999, right? It's like the wide version of an ASCII 9 is 0909, 00390039. And we see that we can put that in memory such that it crashes on our controllable content. But where the protections were put in place, what happens is that piece of memory isn't being freed yet because of delayed free. It's still being hung on to, and it's zeroed out. because one of the things we did in our algorithm is we zeroed out the memory before we finally later let it go. So you get these crashes that look like, in this case, move, ECX, dword pointer, EAX, the contents of whatever EAX contains, and EAX apparently is null, since it's a pointer we're fetching out of our zeroed out memory. So that's pretty typical of a crash that previously, if you had found a crash like that, you might have thought to yourself, oh, this isn't very interesting, it might be non-exploitable. But now when you see them inside IE, if you're running an IE fuzzer or something like that now if you get a crash on a null pointer, you might think to yourself, maybe this is an interesting UAF bug that's just crashing because of delayed free. And there's things you can do about that. I think you can actually disable delayed free, for example, as a registry setting or something like that. So you could maybe just disable it so that you can carry on with your fuzzing as normal. And then we'll look at a few other bugs and see how they did as well. So here's another bug, and I don't really want to spend time to explain what each bug was and what the object was and what the size was, because it doesn't really make all that much difference anyway. I just want to explain the idea that it fixed things in some situations, but not in every situation, is kind of the takeaway from this talk. So this bug is similar to the first in that without the protections, we see that we're able to get the value 11223344, which is just some arbitrary value that we control. We're able to get that into a pointer that can influence execution in some way. But with the protection in place, we again get a crash on null, because the same situation. Memory has been freed, but it hasn't actually been freed. It's just zeroed out and waiting in this basically like a linked list of chunks that'll later get freed by delayed free when there's no more references on the stack. And you can see I'm doing this S-D08000 whatever. That's basically just a search in WinDebug looking for all the places that pointer shows up in memory, and we can see that it showed up on the stack. There were some results where it was found in memory, which means that it won't be released yet until some critical situation. Okay, so in another bug, the third of the four UAF bugs, when we do a search, we see that it's actually not finding any results on the stack, which is really promising. So that's a good thing. So maybe we could get something workable for the third bug. But one thing that's different about it is it's been changed from the default heap to the isolated heap. So it was one of the ones that had its position changed, which is a good thing as far as security goes. So what you need to do is basically you're going to have to use my Python script or some other technique to search through all the allocations available in mshtml.dll that go to the isolated heap that are of that size. But one of the questions I had was, does it really need to be the exact same size as the prior allocation? Because that really limits the potential objects you have that maybe you only have like 4 choices then and only one of them's good or something. Maybe you want to have a lot of choices because you'd like to replace it with an object that you can fully control. The more control you have over the object that you used to replace the one that was gone, the greater the chance of exploitation is kind of the thing there. So let's look at the final bug. And the final bug, if you look at the malicious HTML JavaScript type code that kills the browser, it's basically real similar to the other one where we set up some tricky situation where we allocate an object, we apply the object to the DOM in some way, and then we somehow call some event or listener, or there's some situation that causes a sync issue where we go off and we do something, it gets freed, and we come back and it's gone. So it's very similar in that sense without getting into kind of all the details of the bug. And it's very promising in the sense that at the time of the crash, when we do a search for that object's address, the base pointer of that object, we see that there's no results at all, which is really good. So we could probably do something with it. And then in fact, this one, we were able to bypass both delayed free and isolated heap. And so the question is, it's pretty interesting, how were you able to bypass both those with this particular bug? What was different about it? And the main thing that was different is that this bug was long-lived. So if you think back to how we defeated stack cookies, remember all the way back to the beginning of the talk, I talked about stack cookies. How did we defeat stack cookies? We didn't really defeat stack cookies. We just found a bug that was different such that the stack cookie didn't matter. You know what I mean? So you can many of these protections you can defeat essentially by finding a situation where that protection's kind of basically doesn't matter. And that's essentially what long-lived pointers do. So this pointer lives way beyond the area where the object was originally used. So if you look at the the stack trace, which we can do with that bang heap dash p dash a, in this case ECX is the object we're looking at. If you look at the call stack which led to this object being freed, you can find that, I don't know if you can read that or not, but it did actually go through the protected free routine, but later was actually freed using the NTDLL heap free API, which is the normal API that frees memory. So it eventually really did get freed, and then it's later used after that. And we didn't really have to do anything tricky to set that situation up. That just happened based on the nature of this bug. So that's kind of an interesting thing. Well, one of the other things that's interesting about it, to answer my other question, is does the object that we replace, the original object, have to be the exact same size? And the answer is really no. Because the object that gets used and then freed and then later used again is of size hex 40 on the isolated heap, and the object that we used to replace it was of size 64, which normally wouldn't work, but we'll see why that works. And the way the object is one of these area objects, so you just do document.createElementArea, and then you set its shape to rectangle, and then you can set some coordinates, which is basically 41, 41, 41 in decimal. And the way that works is what's called coalescing, which is kind of an interesting thing that we've been talking about for about 15 years in the security industry. It was used a long time ago to exploit the linkage between heap chunks, basically. You could do a heap buffer overflow outside of the bounds of your heap chunk and overwrite the metadata which described the next heap chunk. And then next time those were both freed, the allocator itself would basically look at the metadata and go, oh, I need to coalesce these two and make them one bigger piece. And you could actually exploit it based on the pointer manipulation that happened in this case. So that's not what's happening here. It's not based on the pointer manipulation between heap chunks, but it's this same idea of, again, the allocator wants to make sure that we're not fragmenting memory. So when it sees a bunch of these hex 40s together and we free a couple of them in a row, it'll go, I can squish some of that space together, wait for that to happen, and then we allocate our size 64 object, and there'll be room in that same spot if we've properly groomed the heap such that that condition is reliable. Variety of things could happen, you know, if some other allocations take place in between or something that might mess up your your scheme, which is why you have to carefully groom it and make sure you do that all in a timely manner so that nothing changes in between. But in this case anyway, you could set up a situation where you can allocate a bigger object, which is kind of nice because that bigger object might overlap the full smaller object, which means you can use the data members to selectively override even the vtable pointer, which is at offset 0 in a C++ object, which is normally hard to control. If you overwrite it with an object of the exact same size, you probably can't control those first 4 bytes, which means you wouldn't be able to selectively overwrite what you want anyway. Okay, so yeah. Basically, to summarize, UAFs are bad. They're fairly easy to exploit, even though they sound really complicated as far as talking about them. You know, basically, if you can figure out the situation, of when it gets freed and when it's used again, you can, allocate some string in JavaScript to be some malicious input. So it's relatively straightforward as far as exploitation is fairly hard these days anyway to begin with. But as far as exploitation goes, it's relatively straightforward. And so from a protection standpoint, how can we make our code safer? If you have to write C and C++ code, what can you do to guard against use after free bugs? Because if you are writing C and C++ code, which a lot of people are actually still, believe it or not today, even though it's like a fairly dangerous language in terms of hard to get right, but if you're doing any embedded system, any kernels, any complicated, any stuff like that, there's still a lot of code being written in C and C++. So we should think about this. What are some of the things you can do? Again, you can use some safer way of managing the life cycle of your objects. Really audit that code carefully. Be careful with that. Maybe use smart pointers if you think it'll help in your particular code base, and maybe even use some of these ideas of using separate heaps for certain objects, because it's actually not that hard to implement. It's not a terribly difficult thing to implement. Even the delayed free thing is not terribly difficult to implement. You can look closely at what some other vendors have done. So what could Microsoft have done in this case to make this a little harder? I think the long-lived dangling pointer is kind of a problem. So because you can't hang on to it forever, you have to actually free it at some point. You can't search like the entire memory space to see if there's some pointer still around before you free, because that would just be too expensive every time you're about to free. So one of the things that they can do, and this is what I think I alluded to at the beginning of the talk, is CFG, which is control flow guard, which is this idea of control flow integrity. And this is something that you're seeing coming out in very modern compilers. Visual Studio 2015 has it. LLVM and Clang have it. So it's this idea of basically saying, if you're about to do an indirect call of any kind inside of a C++ object, so you're going to call a virtual function method from inside this object, you shouldn't be able to call just anywhere in the address space. You should be able to only call to these 3 or 4 pointers or whatever was valid inside of the members of that object. And it's kind of interesting because actually it's basically the reverse of the idea I had, I don't know, however many years ago that was for the Blue Hat Prize contest for some of the research that went into Emmett. My rot protection idea was basically the opposite of that, which is when you return from a function, you shouldn't be able to willy-nilly return anywhere in address space. You should only be able to return to where you came from, essentially. It's that same idea of basically enforcing some sanity on where we either return or call to. It shouldn't just be anywhere in the address space. You can actually implement systems that, enforce the integrity of the calls or returns that take place. The only question is, at what cost, right? How much does that impact performance and stuff? Because we all know when it comes to security, or maybe you don't know, if you've ever worked for a company that develops software, there's, burning customer priorities that we need to ship right away. There's, someday we'll get to this, and then there's security that we'll someday get to later after that. So security is unfortunately generally not priority number one for almost any development organization I've ever seen or been a part of. So so my point is, if this CFI idea sounds great, but if it's like a 10% hit to performance, it's not going to work, right? So it has to be. So they found a way to basically do it in a limited fashion. It's not checking all returns, but it's just checking certain types of indirect calls that doesn't have very much overhead and works pretty well and would limit some of these types of UAF-like attacks. So that's one thing that could be done to deal with these attacks more broadly, instead of just having some isolated protection against, specifically delaying the freeing or something like that. So just to point out the obvious, I was talking about UAF attacks and memory corruption today, there's other memory corruption bugs still out there floating around that could work against your system that are not related to UAF. So just kind of pointing out the obvious there. Yes, you could implement these. And to close, I just had a few short thoughts, I guess, closing. One of the things that's interesting is that, having been in this field for 15 years, you see this cycle of, really complicated attacks being all the rage, and then it's like, well, that's getting really hard for attackers, so let's just go back to calling people and asking for their user pass or whatever. Right? There's easier ways to get into systems, and then you kind of see that oscillate a little bit. And memory corruption's getting, I think, fairly difficult. I think in the next year or two it'll be quite difficult. And so what you'll see is, my prediction anyways, you'll see more of these. Like if you look at some of the CVEs from last year, certainly there were plenty of memory corruptions related to UAFs, but there were also other types of bugs, like from one tab in a browser to the other, you could break SOP, the same origin policy. So you could steal a cookie from, the Gmail cookie from Amazon or something like that. Basically that breaks the model of browsing if you can do stuff like that. And it's not memory corruption. These are all basically logic errors, design flaws, right? Same thing with another flaw, which we saw, that allowed contents of the clipboard to be read from JavaScript, which is bad. You really don't want an arbitrary website to be able to read your clipboard, because God knows what's on there, right? And there was a really interesting talk that the ZDI folks gave last year at Black Hat, where they talked about breaking out of sandboxes using, essentially, at least in one case, they were talking about a non-memory corruption bug technique, which was quite interesting. If you have interest in that, I would highly recommend you go and check out the research they did, because it was some pretty good stuff. And then, so my prediction is a couple more years of memory corruption, kind of still flying high like it's been forever, it seems like. And then you might see that taper off for a while, and then probably you'll see a rise again. And that rise will basically be some innovation in that same space, right? There'll be a whole nother stack buffer overflow, heap buffer overflow, use after free, type confusion, double fetch, whatever it is. There's all these different bugs that kind of pop up throughout the years that'll be popular for a while, until we get something like stack cookies or ASLR and DEP or isolated heap or whatever it is that kind of deals with that category of attack. You'll see that kind of hit hot for a little bit and then go away again. So you'll see that pattern continue. One of the things that's interesting, though, is I think because of the prevalence, like Dave said, this industry is hot and all the companies know it's a problem and everybody's kind of pouring resources into this. So you see the field moving faster, at least than it was historically. So like in 1988, stack cookies came out 14 years later, or stack buffer overflow came out, and then 14 years later we got the stack cookie. So it wasn't the quickest turnaround. Where with UAFs, we see them coming out around 2008, and then we see isolated heap coming out 6 years later. So a little better, we see the potential mitigation cycle happening faster and faster. And we kind of expect that, right? Because the whole digital field is happening faster and faster. And one of the things that I just wanted to point out, though, is that mitigation, though, doesn't come up when there's only like a few isolated attacks taking place, right? So if in 2008, for example, there were like some small number of UAFs in kernels or browsers or whatever, but like not enough to really kind of get anybody's attention as far as like actually, redirecting 5 engineers inside of a company to like actually come up and think about how should we create isolated heap or something like, because that takes time and it takes money and it takes thought. And it takes testing and it takes all this stuff, right, to implement a new protection and roll it in your product. It's not trivial. But usually what happens with these attacks is if you look at, like with UAFs, you see some critical moment where there's a pain point, right? There's a threshold that gets crossed where it's like, okay, these things are really bothering me now. So now we got to do something about that. You'll see that same kind of cycle where until something's painful enough, and that makes sense, right? It makes sense for everybody, right? Like you wouldn't put a key on your car or your front door if there wasn't some need for that. So if there's not really much need, you might not do it. So that's a pretty typical situation that you see in low-level code as well. It's kind of a practical social situation. So anyway, my time is up. And anybody have any questions? About code security or UAFs or mitigations or anything like that? If not, catch me around later today and maybe we can chat or at my training tomorrow and Sunday. So, okay.